Okay, so for this morning, apart from the registered students, there are other students that have requested to join in. Okay, for this lecture or discussion. Okay, so there are several, 2 or 3 other students. Okay, just to let the other students know. Okay, so first of all, for okay, sorry. Okay, sharing. Okay, let's go to practice 2 first. Okay, so for practice 2, okay, this is a make-believe exercise just to show you the effect of the importance, why it is important to do a randomization. Okay, so this is something that I have created. Okay, where we have 3 treatments, A, B, and C, and then the measurements for the treatment. I have dictated this as being A, the measurement, the data is 1, the record, the measurement is 1, B, the measurement or the response is 5, and C is 3. And then there is a confounding factor where the confounding factor is based on the run order. If the run order is 1, then there is no change in the data. Okay, if the run order is 3, then there will be an addition, 5 will be added, 4 will be added to the data. And then if the run order is 2, then 2 will be added to the data. Okay, so after that, I have asked you to do, okay, 3 replications, okay, and then also to do 4 types, okay, of experiments, okay, where the first one is no confounding factor and no randomization. Okay, so no confounding factor and then no randomization, and then no confounding factor but with randomization, and then with confounding factor but no randomization, and then with confounding factor with randomization. Okay, so if we were to look at the first one, okay, where there is no confounding factor and then no randomization, so the results that we will get is the actual results, okay, where it is 1, okay, and then 5, and then 3. So meaning that if there are no confounding factors, then we don't have to do randomization, okay. But that is theoretical, because as we have discussed previously, when we do experiments, there is always the possibility that confounding factors exist, because we are doing something which is novel, which we are not familiar with. And another thing is that in any systems, okay, usually it is multifactorial. So we can only, our understanding is not complete, okay. That's why research is progressing, okay, because our understanding of any system is not complete. Okay, so what it means is that there is always a possibility that there are confounding factors that will affect our results. Okay, but in an ideal or theoretical situation where there are no confounding factors, okay, so no randomization will not affect, not doing any randomization will not affect the outcome of the results. Okay, so similarly, if there are no confounding factors, even if we were to do randomization, then we will still get the actual results, which is 1, 5, and also 3. Okay, so if there are no confounding factors, then whether we do randomization or we do not do randomization, it doesn't matter. Okay, but this is theoretical, because in practical, there is always confounding factors. Okay, there is always the possibility of confounding factors, okay, affecting our results. Okay, so if there are confounding factors, okay, and we do not do randomization, so what will happen is that, okay, we will get this kind of results. Okay, this kind of result. Okay, so we have, this is 1, and then this is 7, and then this is 7. Okay, so you can see that the actual trend or the actual result should be 1, 5, and 3. Okay, but if there are confounding factors and we do not do randomization, we will get something which is totally different, which is 1, 7, and 7. Okay, which is different from this result that is supposed that that is the actual results. Okay, but if we were to do randomization, okay, so there is confounding factor, and then we do randomization, and then what we will get is that, okay, we will have like 2.5 over here, and then 8.3 something over here, and then we will have like 4 point something. Okay, if we were to compare this with the actual results, okay, we will still not get the actual values, but okay, you can see that the trend is similar. Okay, and compared to this one, which is totally different. Okay, so if you, this is just to show to you that, okay, that if you were to do randomization, then we will get a better estimation of the actual results. We will never know the actual result because we will never be able to measure all the population, all the individuals in the population. Okay, it is different compared to the exercise that you do, practice 1, where you are able to measure each and every individual in this class. Okay, because it is limited, only 9 or 10 students. But in the actual world, okay, when we are doing studies on actual populations, okay, it is impossible to measure each and every individual. So the actual average we will never be able to get, but what we are trying to do is to get a good estimation. Okay, so without randomization, then it will affect our result. Then we will conclude that, okay, there are no differences between treatment B and treatment C, which in actuality treatment B is higher than treatment C. Okay, but if you were to do randomization, then at least, okay, even if we can get closer to the actual values, where the A is the smallest, is the lowest, and then B is the highest, and then C is in the middle. Okay, okay. Any questions? Okay, so this is just to demonstrate to you. Okay, remember, this is not, I did not do this. Okay, so this is one of you did this. Okay, so, and I'm sure that most of you will get similar results, although there is no guarantee. Okay, sometimes even with randomization, we will not get something similar to the population. That is why even with randomization, remember the basis of statistics, it is based on probability. Okay, it is not an exact, okay, determination. Okay, so that's why even the most we will be able only to conclude or to decide based on a 99% confidence interval. We will never have 100% confidence interval because it is based on probability. Okay. Okay, so that is why in when you are doing your studies, okay, it is very important to do randomization. Do not apply your treatments in a sequential or in a systematic order. Okay, you have to randomize. Okay, any questions? Okay, so if there are no questions, then we'll go to practice 3. Okay, so practice 3 is basically just to show you how to conduct, okay, or how to plan for your experiment, okay, using different types of design of experiment. Okay, so the first one that you are asked to do is how to conduct a completely randomized design. Okay, remember, a completely randomized design is for one factor experiment. Okay, so one factor experiments, and then when we say that completely randomized, so meaning that all the samples, okay, all the experimental units, okay, has to be totally randomized. Okay, so in this case, you have a one factor experiment where the factor is temperature, okay, and then you have how many levels? You have 3 levels, that is 60, 70, and 80 degrees C. And you also have, and because this is a one factor experiment, the number of treatments, the treatments are the levels. Okay, so the treatments are 60, 70, and also 80 degrees C. Okay, so meaning that, and then you are doing 3 replications. So in total, how many samples? You have 3 times 3, that is 9 samples. Okay, so you have 9 samples. Okay, so you have run order consisting of 9 samples over here. Okay, and then you have to totally randomize all the 9 samples. Okay, and this is depicted over here. Okay, where you can see that there is total randomization between the heating temperature, where it is not in a systematic order, and also you can see that the replication is also totally randomized. Okay, so this is a signature of a completely randomized design, where you can see the the treatment and also the replication is totally randomized. Okay, so that's why it is named a completely randomized, okay, design. Okay, and then for the same example, okay, you were asked to do a randomization for completely randomized block design. Okay, so taking the replication as the block, okay, then we have to randomize. Okay, so for this one, it is also completely randomized, but only within the block. Okay, that's why it is called a completely randomized block design. So for us it is not necessarily, for us in food science, it is easier to take the replication as a block. Okay, it's more practical. Okay, because we are lab based. Okay. Okay, so taking the replication as a block. So we do the first block, basically the first rep. Okay, so we do the first rep. Okay, so you can see over here. Okay. Okay, so you can see over here. So the replication is only 1. There is no randomization. Okay, but within the block, within the replication, there is randomization over here. Okay, so you can see over here, there is randomization, okay, between the temperature. Okay, and then similarly for the second block, the second rep, okay, you can see that there is randomization, and this randomization, okay, is different from this one. Okay, the sequence for replication 2 is not similar to the sequence in replication 1. Similarly, the sequence in replication 3 is not similar to the sequence in replication 2 or 1. Okay, because we randomized it. If we were to pick straws and then randomly we got the sequence similar to 1 or 2, rep 1 or 2, it doesn't matter. Okay, but that the chances of you getting that is quite remote. Okay, but if you do get it, then it is okay, as long as you have followed the procedure. Okay. Okay, so you can see over here. Okay, so overall you can see that there is no randomization for replication. Okay, but there is randomization for heating temperature. That is the signature of a completely randomized block design, where there is no randomization between reps. Different, okay, when you compare it to completely randomized design, where there is total replication, total randomization among the replication. That's why it is called a completely randomized design. But for completely randomized block design, the complete randomization is only being done within the block itself. Okay? Okay, so that is randomization over here, randomization over here, randomization within the block. Okay, the sequence is not the same. Okay, so if you were to see that, okay, the replication is not randomized, you can suspect that this is a block design. Okay, and then look at the heating temperature. Okay, any questions?
Prof, I have one. I
Yeah.
have two questions here actually.
Okay.
Like before this, you said that replication is like for the banana example, right? The first
Mm-hmm.
replication to be taken from January, second replication mid of year, and the last replication is end of year.
Mm-hmm.
So for each replication, do we still need to do triplicates for each replication, or uh, those three replication is enough already?
Okay. Okay. The answer is yes and no. Okay. It depends on. Okay, I'll stop presenting here. Okay, so it depends on your objective and also the nature of your sample. Let me share screen. Okay. 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 So sorry. Okay. So remember the banana example. Okay. Okay. So the banana example. Okay. So when we say replication, okay, when we say that replication, okay, so for example, when we want to look at the for the banana example, we want to determine the moisture content of bananas. Okay, so we want to do a completely randomized design. Sorry, a completely CRBD, completely randomized plot design. Also, so we are doing CRBD. Okay, so we have bananas. Okay, and then we have 3 reps. Rep 1, and then rep 2, and then rep 3. Okay, for example, we have also we want to look at the moisture content, for example, for drying the bananas at different temperatures. For example, 60 degrees C, 70 degrees C, and 80 degrees C. Okay, so it's a one factor experiment. The factor is drying temperature. The levels, we have 3 levels, which is 60, 70, and 80. And remember, for one factor experiment, the treatments are the levels. So the treatments are 60, 70, and also 80. Okay, so for the first one, rep 1, so we will subject it to 60, 70, and 80, similar to the second, similar to the third. Okay, the question is, how many samples do we need to do? Okay, so what you have to do, what you must do is, from over here, for rep 1, take 3 bananas only. So 1 over here, 1 over here, and then 1 over here. So that is considered as one replication. Okay, and then over here, you take, when you do your second replication, 1 over here, 1 over here, and 1 over here. So that is considered a one replication, the second replication. For each replication, you have to cover all the treatments. Okay, but if you prefer, okay, you want to do more. Okay, so you want to do, as opposed to 1, you want to do, okay, as opposed to 1, then you want to do more than 1. Okay, So you want to do 2 over here, 2 over here, 2 over here. You want to take 2. Okay. Also, it is also allowed, but you have to average this out. Okay, you have to average this out. Okay, and this is what we call as subsamples. This is what we call as subsamples. So you call this as subsampling. This is not the first rep. This is not a replication. This is not a second replication. No. The second replication is over here. This is the second rep, not this one. This is still the first rep. Even if you were to take 10 bananas, this is only rep 1, but with 10 subsamples. Okay, and then you average this, you get one number and average. This is for rep 1 only. This is not for the whole experiment. No. Okay. Okay, so when do we do this? Okay, when do we have to do this? Okay, it depends on the degree of variability in your samples. Okay, degree of heterogeneity. Remember, okay, when we discuss about the normal distribution, okay, if it is sharp like this, then the majority is at the average, the majority of the population at the average. Okay, very low number of population is at the two extremities. Okay, then meaning that there is a very high probability that when we take an individual from the population, then it is very close to the population mean. This is what we are trying to do, estimation of the population mean. Okay, for example, like if you want to take this example, the drying, okay, the moisture content of the bananas after drying at different temperatures. So meaning that, okay, the majority, if we were to take this, moisture content of, for example, after 24 hours of drying, it is 30%, for example. Then the majority you will get, the majority of the sample will be close to 30% because this is the population average. Okay, so we call this as low heterogeneity, low variation, or low heterogeneity. So meaning that, okay, if you were to take 2 samples, then we will get a good estimation of the population mean. But if, for example, like here, okay, so there are the peak is not sharp, okay, the curve is not sharp, okay, then it is quite it goes up slowly, but the majority is still near the population mean, right? Then you say that, okay, for me to get a good estimation of the population mean, okay, then I need to take more samples. Okay, so maybe 3 samples. Usually in food science, based on consensus, we take 3 samples. So meaning that it is 3 replications, right? Okay, okay. But if we have something like this, okay, so it is still the same value. Okay, but now you see that this is quite a lot, meaning that this is more variation. Okay, it has more variation. Then you need more samples to get close to the population mean. So that is where subsampling comes in. Okay, okay. Subsampling meaning that if you take rep 1 bananas, for example, you take one tandan. Okay, so you have a lot of bananas. Okay, you have 1 tandan. Within this tandan, okay, you feel that it is not that homogeneous because usually for bananas, okay, within a tandan, okay, you have you have differences. So you are concerned about it. If I were to take just one banana, then it will not represent this replication. So you take more, you take subsamples. But if you feel that the heterogeneity is more in the population, then you do more replication. Okay. So so it depends on where you are concerned the heterogeneity is. Okay, because remember the basic principle is that we want to get a good estimation of the population mean. Okay, Anissa boleh?
Boleh Prof. Tapi okay, let's say lah kan, kita nak tahu yang whether that sample is heterogeneous or not, we need to carry out the testing first, right? So let's say the first time we take the 3 samples and we found out that it is very heterogeneous.
Okay.
Then we carry out another experiment. So can we still use the first experiment results to be combined with the second experiment?
Okay. It depends on which one. If you are doing like this, you do the first one, you do the second one, and then you find out that it is quite heterogeneous, then you can always add 3. Right, 4. So you can just add because it is still being within this one. Okay, so I'm doing this one. Okay. But if you have done this, okay, have done this, and then you do 470. Sorry, for example, you do this first, and then you randomize. Okay, this is the run order 1, this is run order 2, this is run order 3, for example. Okay, and then bila you dah, after you have done 1, 2, okay, 3, and then after 3, then you found out that, oh, okay, this is there is high heterogeneity. Okay, the rest you have done 1, 2, 1, 2. Okay, so ideally, then you should, I would prefer to redo this. Okay, or you can add 3 and 4, but then you have to follow this one. Okay, so follow the run sequence. Okay, remember, because we want to maintain the randomization. Okay.
Okay, but still need to be done on the same day juga lah kan?
Preferably.
Preferably lah. Okay.
Unless you have scientific justification that say that, okay, if you were to do another time, then there are no confounding factors that will affect the outcome. So because remember, in science, everything has to be justified, because the basis of science is proof. Okay, so we have to prove it. Whenever we make a decision, we have to prove it. Even when you are writing your thesis, each word has to be justified. Okay.
Okay, Prof.
Okay.
Can I have another question?
Yeah, sure.
Sorry. Okay. Okay, like for my research, it needs to be done chef life study. Okay. So chef life study will be done on day 147, something like that lah. So let's say and then for the chef life study need to do 2 testing, and let's say this another one testing need about 4 hours. So if 4 hours, the maximum
To
I can
testing meaning 2 responses.
yes, 2 responses.
Okay.
Okay. PV and T bars.
Okay.
For example, right? Okay. So for example, T bars need 4 hours of total experiment. So the maximum I can do the testing for only 2 replication can be done for one day. So the third replication, I might cannot do on the same day. Is it uh, is there any way to, because right now we learn that completely randomized block design, we block the replication, right? But still preferably all the replication must be done on the same day. If I continue tomorrow, it will be day 2 already. So
Okay.
do I need to, is it okay if I do another batch of uh, let's say for this one is burger, right? Burger store at day 1, day
Mm-mm.
4 and 7. So I start storing today. Then I do another set. I start storing starting tomorrow. Is that
Uh,
okay?
okay.
Mm-hmm.
Actually, if it is justified that that you that what you are doing is not going to affect the outcome, then it is okay. It is not necessary for you to always do everything within the same day, unless it's going to affect your outcome. Then you have to do it. Okay, doing everything within the same day is just an example. Okay, so when doing storage, okay, actually the ideal way of doing storage is like, for example, if you have like a one, there are two approaches. Okay, so this is day 0, this is day 0, this is day week 1, for example. Okay, just take a longer time. Okay, and then this is week 2. Okay, so week 1 and then week 2, for example. Okay, so this is week 0. So we put in a sample, and then after 1 week, then we sample. After 2 weeks, then we sample. Okay, so that is one way of doing it. Okay, another way of doing this is, so we put in several. So this is for week 0, then we sample it. This is for week 1, and then we sample it. This is for week 2, and then we sample it. Okay, so it depends, but as far as for this one, the randomization is not this is basically, it is like more of a CRD. Sorry, you want to do a CRBD, so this is for rep 1, right? Is it, Hanisa? Macam ni ke?
You go.
Okay, so uh, so there are the two ways of doing this. Okay, I would be more comfortable using this method, this approach, as opposed to this one. Okay, because with this one, then you start to interfere with the system, over here. Okay, so but sometimes you cannot get away from it. For example, if you have a fermenter, then you cannot have 3 fermenters, right? So limitation of equipments, then you have to do it. But if not, then I would prefer to have this kind of approach. Okay, so the question is that you need to if you take a sample over here, then you need 4 hours to analyze the data, the sample. Okay, so remember, design of experiment is regarding the application of treatment, not the analysis. Okay, remember? Okay, so meaning that when you do for you is food packaging, right? For burger. Okay.
Yes, yes,
Okay, so you apply different types of packaging, if I'm not mistaken.
yes.
Is it? Okay, so you have, for example, 3 types of packaging. Okay, so this is rep 1. So you have 3 types of packaging. You put it inside the chiller, and then after week 1, you take week 0, you analyze. Week 1, you analyze. Okay, you said that it is day 1. Sorry. Okay, day 1. So meaning that you are concerned that you do not have enough time. right? Okay,
Yes.
but remember, the DOE is about the application of treatments, not about the analysis. So even if you don't have enough time for analysis, it doesn't matter. Okay, as long as you can preserve your sample. Okay, for example, you are more on oxidation, right?
Yes.
Your PV and T bars.
Yes.
Okay, so after day one, you take out the sample and then you can freeze it because and then you can freeze it or you can vacuum pack it. So there will be no oxygen and then freeze it. So there is enough literature that you can justify that when you do this, then it will not affect your PV or T bars. Okay, so you don't do the analysis directly, immediately. You just vacuum pack it and then freeze it, put it in the freezer, -20, for example. Okay, and then on the day after day one, day two, then you do the same thing. Take out the samples, okay, and then you vacuum pack it, and then you freeze it. Okay, so when you have the time, okay, you can just analyze it one at a time or all at once. Okay.
Okay, Prof. Thank you.
Okay, so remember, it is not about the analysis, it is about the treatment. Okay, you can do all the analysis at once, okay, after you have finished the treatment, but application of the treatment, then you have to follow the DOE, because we want to have a level playing field. We do not want to have any confounding factors affecting our results. Okay.
Okay, Prof. Thank you.
Okay, welcome. So any other questions? Even students that are just listening in, okay, if you have questions, you are welcome to ask.
Doctor, I have a question, a quick one.
Okay. Okay. So if there are no questions, then
Doctor, I have a question. Can I ask?
yeah, sure.
Okay, just a quick one. Just now, when you showed the CRBD, the block design, okay, let's say there's another situation where we have two factors, but the treatment is only one, meaning one temperature only, 60 degree, and then but we have the another factor which is time, which has three levels, 10 minutes, 20 minutes, 30 minutes. So two factors. The
Okay.
treatment only one, which is 60 degree. Time three types of time: 10 minutes, 20 minutes, 30 minutes. And then we want to do replication by block, meaning rep one, rep two, and then rep
Okay.
three. So,
You want to the right as well. Okay.
yeah. So is that considered as CRBD as well? Imagine
Okay.
we put inside the water bath only one temperature, 60 degrees Celsius. We put for rep one, we put all three beakers, 10, 20, 30 minutes. After 10 minutes, we take out. And then after the 20 minutes, we take out the second one and the third one.
Okay.
Is that considered
Okay.
as CRBD?
Okay. So you have two factors, right?
Yeah, two factors.
Okay. So the first one is temperature.
Temperature, only one level.
Second one. Second one,
Time,
time.
time. Mm-mm.
Okay. So for the temperature, you have
Only 60 degrees.
60 degrees C. For the time,
10 minutes, 20 minutes, 30 minutes. Let's just say.
okay, 30 minutes. Okay. So if you were to look at this, okay, actually how many factors? What is the definition of factor? Factor is something an aspect that we want to investigate. Okay, when we want to investigate the effect.
Mm-mm.
How do we investigate the effects? We have to vary it by taking this one 60 degrees C, then actually it is not a factor because it is constant. You can never determine the effect of temperature because you only use one. Okay, goes on.
Uh-uh.
So meaning that this is actually a one factor.
Oh, okay. All right.
So your factor is time. Okay. So for
Uh-huh.
example, if you have a water bath, okay, and then this is 60 degrees. Okay. So this one is 60 degrees C. Okay, and then you put in your this one. Okay. Okay. So and then after this is similar to this one, where you have after 10 minutes you take it up, after 20 minutes you take it up, and then 30 minutes you take it up. Okay.
Okay.
So the problem is,
We want to do by block, meaning rep one first. Rep one,
okay,
30 minutes, rep one, 10 minutes, rep one, 20 minutes, for example. And then after that, we do the rep two, and then we do the rep
mm,
three. We do it
okay.
by block.
Okay, for this one, you can do it. For example, you have like 3 samples over here for each rep. So you do it, your first rep, and then this is for uh 10, 20, 30. Okay. What is the so you prepare your samples and then you put it in the water bath, is it?
Yeah, yeah.
Okay. So you can put it in the water bath. Okay. After 10 minutes, after 20 minutes, and for 30 minutes. Okay.
Yeah.
So
This
when
is rep
you
one.
this is rep 1, and then you can repeat it for rep 2, or you can do a complete randomized design if the space is enough. This is the water bath, right? For example, this is the water bath. Okay, so you have 3 times 3 equals to 9. Okay, so you can put it inside the water bath. Okay, but do not put it for example, this is a completely randomized design. Okay, so you have 9 samples. Don't put in all this, put everything in, but when you want to determine, okay, so you label the beakers, okay, as similar to randomization. Rep 1 10 minutes, rep 1 20 minutes, etc. Then you put it randomly over here. Okay, so
But that's the
then
problem, doctor.
yeah,
If we put all of it, then it's all going to be sequential. Then I don't understand where the randomization is at, because we already labeled it. We know what time we want to take it out. It's sequential lah.
as long as you put it not in an orderly manner. For example, this is not rep 1, this is rep 1, and then this is rep 1. You put this, for example, rep 1 10, this is rep 2 20, this is rep 3 30, and then this is rep 3 10. See that you just mix them up.
Oh, it's still considered random, meaning it's still
Yeah.
considered random, even just playing around with
uh,
where they put, even though we put it at the same
yeah.
time in the water bath.
Yes.
Oh, okay, all right. I
Yes.
thought I
Yeah.
thought it was
So,
sequential.
but this is CRD. But if you want to do a CRBD, similar, but you only have 3. Okay. So you only have 3, but you don't do it like every time this is for 10, every time this is for 20, every time this is for 30. Okay. Always have as much randomization as possible when applying your treatment.
Okay.
Okay.
All right, got it.
Okay. Any other questions? Okay. So if there are no questions, then we'll go to okay. So we'll go back to our practice. Okay. Okay, let's take a look at practice 4. Okay, so for practice 4, it is for a factorial design. Okay, a factorial design meaning that you have more than one factor. Okay, 2, 3, 4, and so on. Okay, so now you have two factors. In this practice, you have two factors, heating temperature and also heating period. Okay, so what happens is that for this one, I want you to do it to do the randomization based on a completely randomized factorial design. Okay, so remember, okay, for this one, you have two factors, that is heating temperature and heating period. Okay, and the levels, okay, for heating temperature, you have three levels, 60, 70, and 80. And for heating period, you have also three levels, that is 0, 20, and 40 minutes. Okay, the treatment, okay, so you have two factors, three levels each, and the treatment is 3 times 3, that is 9 treatments. Okay, you have 9 treatments. Remember, for more than one factor experiments, okay, the treatment is the combination of levels. For one factor experiment, the treatments are the levels. But for more than one factor experiment, the treatments are the combination of the levels. Okay, so you have 3 levels for temperature and 3 levels for heating period. So the combination is 3 times 3 equals to 9 treatments. Okay, the number of experiments or the number of samples that you need to prepare is, you have 3 replications. So meaning 9 treatments, 9 times 3, meaning 27 samples. Okay, so when you prepare your run order, so you need to have 27. Okay, so for completely randomized factorial design, okay, as in completely randomized design, okay, so all the samples, all the 27 samples have to be randomized. Okay, so you can see that total randomization for replication over here, total randomization for heating treatment, heating temperature, and also total randomization of heating period. So if you were to look at this, see this, then you know that this is a completely randomized factorial design. Okay. Okay. Another design is randomization. Okay, sorry, factorial design with blocks, similar to completely randomized block design. Okay, so in this example, we are taking the replication as blocks. Okay, the replication as blocks. So, sorry. So you can see that there is total randomization of the heating temperature, total randomization of the heating period, but only within the block. Okay, only within the block. So when you look at the replication, there is no randomization. It is rep 1 first, and then rep 2, and then rep 3. Okay. Okay, so you can see this, that for heating temperature, okay, so there is randomization. For heating period, there is randomization. And the randomization, sorry, and the randomization, you can see that for the heating temperature, okay, for rep 1, it's not similar to rep 2. Similarly, for heating period, for rep 1, it's not similar to rep 2. Okay, so that shows that there is randomization. Okay. Okay, any questions regarding the practice 2, 3, or 4? Okay, if there are no there are no questions, okay, so we'll take a break, 5 minutes break. Okay, and then we'll continue at 10 o'clock. Okay, with presentation, okay, from Norin. Okay. Okay, so what we'll do is that, okay, Norin will present, okay, for 5 to 10 minutes. Okay. Norin will present for 5 to 10 minutes. Okay, and then after that, I will give 5 to 10 minutes for all of you to ask her anything that you are not clear, okay, regarding experiment, not technical, but statistic wise. Okay, anything that you are not clear. Okay, and then she will have to answer all your questions. Her answer may be right or may be wrong. I'm not going to comment on it. Okay, so meaning that you have to determine whether the presenter is giving you the right answer or the wrong answer. You have to decide. Okay, so this exercise is for you to decide on your own. Okay, and then after that, I will give you a quiz. Okay, you have to answer. It is a very short quiz, very short answers. Okay, 5 to 10 minutes. Okay, and then after that, we'll discuss the answer. Okay. Okay, so we'll take a 5 minutes break. Okay, we'll come back at 10 o'clock. Okay, so we'll continue. Okay, just to add on what I have said just now. Sorry. Regarding what Kausar has asked just now. Okay, so remember that when we have a water bath, okay, like this, okay, even though we set it at 60 degrees C, okay, the temperature at different points will vary. Okay, so it will vary. So whether it varies a lot or it varies little, so it depends on the equipment. Okay, it depends on the equipment. So that is why the ideal way is that we have a water bath, and then at one time we put in one sample, and for the next sample we always put in at the same spot. So then we can be sure that okay, all the samples is being exposed to the same temperature profile. Okay, so if you were to put in, okay, like this one, usually the water bath, it has a heating element here, and then there is a pump. It sucks in water and then pumps it up. The water will go through the heating element and then it pumps out. So this is lower temperature, this is higher temperature, right? Okay, so when we put in a lot of samples or a few samples, then over here the temperature will be the highest. Over here the temperature will be the lowest. Okay, so there will be a variation of temperature within a water bath, even though we try to minimize it. So that is why even within a water bath, we should not put in too many samples, because we have to balance the heating, the heat supply, okay, and also the heating load. Okay, so that there will not be too severe a drop of temperature. Okay, so usually when we do heating experiments, the first step is to do a temperature profile. For example, if we plan to put in 3, okay, if we plan to put in 3 samples, okay, so in food engineering, usually we will put in the samples and then we will measure the temperature profile over time. Okay, over time. Okay, whether usually you can see a drop and then only an increase. So at different points, we want it to be approximately the same. If we have that, then we can justify that, okay, there are no temperature variation between these points. But if you do not plan to do it, my advice is to randomize. Okay, because it may be a confounding factor, the different temperature profiles. Okay. Okay. So let's go to our first presentation. Okay. Okay. Okay, so the first presentation will be from Noreen. Okay, Noreen, please share and then present for 5 to 10 minutes.
Assalamualaikum.
Salam.
So for today, I will present on the journal title, Evaluation of the Use of Pequi Pulp Flour in Breaded Meat. Okay, the problem statement is processed meat food may be associated with poor eating habit, but the aggregation of vegetable ingredients such as pickle makes the formulation of this product healthier and more nutritious. Pickle is a fruit native to the Brazilian Cerrado, physically characterized as a green to greenish brown leathery apical fruit, and inedible external mesocarp of white color with internally from 1 to 4 pyrines composed of an edible mesocarp, orange yellow, and a seed or almond coated with a spiny wood endocarp. The pickle pulp has a rich composition with an emphasis on the content of mineral, fiber, ascorbic acid, carotenoids, phenolic compounds, and fatty acid. In relation to minerals, the pulp can be associated with high content of zinc, magnesium, and copper, as well as being source of phosphorus and iron. It is also worth mentioning a high content of dietary fiber in the pickle pulp, which are known to be beneficial for gastrointestinal health and in the control of obesity, diabetes, and blood pressure. So the concern for healthy eating has grown in view of the association of health problem with the exacerbated consumption of industrialized food, which are low in nutrients and without compounds or functional ingredients. In an attempt to reverse this scenario, some research is being developed to produce healthier, quick meal products without, however, greatly affecting their technological quality. So, based on pickle feature and the need to create healthy food and with attributes that please the consumer, this research aimed to carry out chemical characterization of breaded chicken prepared with pickle pulp flour in the breaded layer, as well as to evaluate the technological and of the breads produced. So the objective of this research is to characterize the chemical composition of breaded chicken prepared with pickle pulp flour in breading, as well to evaluate the technological and sensorial properties of the breaded chicken. So this is the experimental flowchart. There are three steps in the research. The first one is the development of pickle flour. Uh, First, the ripe fruit, uniform size, intact skin without mechanical injuries, stains or cracks are used. Then the fruit will wash, brush and sanitize in sodium hypochlorite solution at 100 milligram per liter for 30 minutes and bleach in water at 90 degree for 5 minutes. Then peeling, removing the pyrines and removing the fruit, fruit pulps was performed manually. The removed, the removed pulp was immersed in sodium hypochlorite solution at 50 milligram per liter for 30 minutes and then cut into standard size. After that, second step is flour preparation. The pulp was directed to a dryer with forced air circulation at 60 degrees C for 6 hours. Then the dehydrated pulp was cooled to room temperature and subjected to grinding in a domestic multiprocessor until the desired granulometry was reached. The flour was then placed in a tightly closed glass container and stored at 7 degrees C. The last one is the breaded chicken formulation. For breaded chicken formulation was prepared. BC is the breaded control, B25, B50 and B100, which differed by the composition of the breading ingredients from the pre-flooring stage, which means B25 is using 25% of pickle pulp flour, B50 use 50% of pickle pulp flour and B100 is 100% using the pickle pulp flour. In the formulation of the breaded control products, for the production of breaded, chilled chicken breast fillet were ground in grinder. Then the fragmented meat was mixed with the other ingredients of the formulation. The homogeneous meat mass then mold to form the shape of the nuggets. After molding, the products proceeded to breading, which was carried out in 4 stages. First one, immersed in batter liquid. Then second, pre-flour with butter BC flour or PPF, pickle flour, or combination thereof, butter again, and then flouring with cornmeal. Breaded products were packed in polyethylene bags and stored at -2 degrees C. And lastly, the breaded products were fried for 4 minutes in soybean oil at temperature of 170 degrees C to 180 degrees C. So there are 3 types of analysis conducted: chemical composition, technological properties analysis, and sensory analysis. For the chemical composition, this research is conducted to determine moisture, ash, lipids, proteins, and total carbohydrates. While the technology properties analysis conducted is to determine the specific volume, raw and fried, percent of mass yield, color difference, chromaticity, and tone of breaded chicken. And sensory analysis are consumption intention and acceptance, which comprise of appearance, texture, flavor, and overall acceptance. For the design of experiment, this research is conducted under the completely randomized design. And the factor used for this DOE is composition of pickled pulp flour in pre-flooring stage or pre-dust, BC, B25, B50, or B100. And this research used 3 replication, and for each replication there are 12 samples. For BC, 3 samples, B25, 3 samples, B50, 3 samples, B100, 3 samples. So overall for each replication comprised of 2 samples. And the statistical test involved is analyzed by SISVA software, and the statistical tests are using ANOVA. And when significant, the Tukey's test is conducted with the significant test level at 95%. So the conclusion of the research is the use of pickled pulp flour in pre-dust layer of breaded chicken adds nutritional value to this product, mainly increasing the lipid and protein contents. While in the technological evaluation, pickled flour
Norin,
yeah,
Norin, conclusion tak perlu.
okay. So that's
Uh,
all from me. Thank you.
okay, thank you, Norin. Okay, so Norin, please show the experiment design slide before that.
Okay.
Before this one. Okay, this one. Okay, thank you. Okay, so all the students, okay, you have 5 to 10 minutes to ask Norin about statistics only, okay, not about the technical aspects, okay, regarding this study, okay, because I will give a quiz based on the information, the statistics from this study. Okay, so if you have anything that you are not clear, you can ask her now. After this, you cannot ask her anymore. You have to answer the quiz. Okay, so any questions?
Doctor, I have a question.
Okay, please.
In the slide, there's mentioned there are 3 replications, and then one replication have 12 samples. Does it mean that there are 36 samples in total?
Yes.
Okay, thank you.
Okay, any other questions? Okay, so no other questions? Okay, so if there are no questions, okay, so thank you, Noreen. I will share. Okay, I will share. Okay, I will share the questions. So what you need to do is answer the questions. Okay, it's up to you whether you just want to write it down. You don't have to write down the questions. Okay, just write down the answers. Okay, so write down the answers and then take a picture and then send to my WhatsApp it to me. Okay, so you can do that, or you can also do it on paper, okay, in your computer, and then email it to me. Okay. Okay, so I will present. Okay, so for the, sorry. Okay. 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 So that is the question. Okay, this is open book. Okay, you can open, refer to your books, to your notes, even to the internet. It's just that you should not discuss between yourselves. Okay, so you have 10 minutes from now. Okay, so please answer and then email your answers to, okay, email to Yusuf M at ukm.edu.my. Okay, name your email. Okay, as STKM 6122. Okay, quiz 1. Okay. Or you can just snap a picture of your answer and WhatsApp to 01927389995. Okay, so make sure that you have your name, okay, and metric number, and the name of quiz. Okay.
Prof,
Yes.
kita nak hantar dekat Prof lepas habis jawab semua orang punya presentation atau each satu quiz hantar, satu quiz hantar?
Satu quiz hantar.
Okay.
You have to submit your answer within the 10 minutes that I'm giving you to answer.
Okay, Prof.
Okay.
So the question,
Yes.
this one is only the first question only. Okay?
Sorry, tak dengar.
So, soalan satu tu sahaja ya.
Soalannya satu saja. Only one question.
Okay. Alright. Thank you.
Okay. Sorry. Actually ada dua. Actually it has two questions. Saya tersilap. Okay, tadi yang tanya siapa? Hajar ke? Ya, okay, sorry ya. So saya tambah lagi 2 minit. Okay, masa telah tamat. So sila submit jawapan. Ada lagi 2 pelajar belum submit. Okay. Seorang lagi. Ajar. Ajar Ashikin. Sila submit dia punya jawapan.
Ada terima tak, Doktor?
You hantar email ke ataupun apa?
Email.
Ataupun email. Email tak ada lagi. Okay, baru masuk. Okay. So ajar Okay, so semua dah submit. Okay. So okay, saya akan share di sini. Okay, so ini adalah paper yang Norin present tadi. Okay. Okay, so basically, okay. Okay, so kalau kita lihat di sini, okay, apakah dia punya, ada berapa faktor? Okay, so jawapan dia adalah cuma satu faktor saja. Okay, so jawapan dia adalah cuma ada satu faktor saja. So macam mana kita nak tahu faktor? Okay, remember the basis of experimental design is that everything has to be constant except the factor. Okay, so that is the most basic principle. Okay, everything has to be constant except the factor. So if you want to look at which is the factor, then you only have to determine which parameter or which aspect is not being maintained as constant. Okay, so a factor has to be could not be a constant. Okay, so remember, like the example that Kausar gave just now. Okay, so if it is constant, then it is not a factor. Okay, so in order for us to determine the effect, we have to vary the factor. Then only we will be able to determine the effect. Okay, so in this case, okay, so the factor is only one. Okay, which is the braiding, BC, B25, B50, and also the B100. So that is the factor. Okay. Okay, so the factor is the braiding. Okay. And what are the levels? How many levels? The levels, you have 4 levels, which is levels or type, which is in this case, it is a type. Okay. So it is BC, B25, B50, and B100. Okay. So the factor is the composition of PQ pulp flour. Okay. And then what are the treatments? Okay. This is a 1-factor experiment. So the levels are the treatments. So the treatments are BC, B25, B50, and B100. Okay. So how many replications? We have 3 replications. Okay, 3 replications. And in this case, we have subsamples. Okay, we have subsamples. So for each replication, for each treatment, they are using 3 subsamples. So meaning that in one replication, they will have 3 samples of BC, 3 samples of B25, 3 samples of B50, and 3 samples of B100. So in total, 4 times 3, sorry, 4 times 3 is equals to 12. So within one replication, they have 12 samples. Okay, so in total for 3 replications, they will be having 36 samples. Okay. Okay, so the factor is the independent variable. It is also known as an independent variable. Okay, the responses are the dependent variable. Dependent meaning that the response in our hypothesis, the response will be affected by the factors. So that is why the response is being named as a dependent variable, whereas the factor is being named as an independent variable. Okay, so the response are the aspects that we are measuring. In this case, we have how many responses? Okay, we have chemical composition have 1, 2, 3, 4, 5 responses. Technological properties also have 5 responses. Sensory analysis, we have 2 responses. So all of this, all the things that we are measuring, that is the response. Okay, so remember the factor is the aspect that is changing. Okay, if it is constant, it is not a factor. Okay, and then you have the levels or type, and then you have the treatments. Okay, and then the replications and the subsamples. Okay, if there are any. Okay, and then we have the responses. Responses are the aspects that we are measuring. Okay, so the question is how many factor? The answer is 1 factor only. And what are the factors? Okay, so in this case, it is 1 factor. So what is the factor? It is the composition of liquid pulp. Okay, so that is the factor. Okay, any questions? Okay, so everyone is clear? Okay, good. Okay, so so now, okay, we'll go to the second presenter. That is Kamarina. Okay, so for today we will it's 10:50 already. Okay, okay, so we won't have time for the second presentation. Okay, so we'll stop here, and then we'll for Kamarina and also Hanisa, right? Okay, so they will be presenting next week, and then followed by Shafika and Farhan.
Prof, the reason I changed with Mus Yuyan for this week is because I cannot present next week because I have to attend a conference.
Oh, Kamarina, right. Oh,
Yeah.
okay. Sorry, I forgot. Okay. So then in that case, so for next week, we'll proceed with Hanisa and Shafika and Farhan and Siu Yen. Okay, so Kamarina, you have to be bumped to the on the 21st. Is it okay?
Yeah, okay. All right.
Okay. Okay. Is everybody okay?
Okay, doctor.
Okay. Okay. So we'll stop here. Are there any questions? Okay. So no questions. Everybody is clear. Good. Okay. So we'll stop here, and then we'll continue next week, inshallah. Okay. So thank you, everybody.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.